Hello, everybody. My name is Vijay Jasankar, and I'm affiliated to the International Institute of Information Technology, Bangalore. And today, I'm very excited to be presenting our work, SuP-SLiP, subsample processing of large-scale LiDAR point clouds. So let's have a look. Now, the intentions and the notions of autonomous driving and point cloud need no introduction. There has been increasing attention to these very important fields of passenger mobility, driver safety, and overall road usage. To this end, one of the key tasks in point cloud processing for autonomous driving is road segmentation, which we formulate as follows to compute the road points in a static large scale MLS LiDAR scan. So as you can see over here on the right, this is from the famous Toronto 3D dataset, and the road points in dark blue here correspond to a majority class in the dataset. And these kind of tasks to determine which point belongs to which class is typically solved through semantic segmentation models. What we can notice is that in literature and in industry, there's a big disparity between the number of models and the number of datasets. As we know, deep learning models are quite data hungry, but due to the cost of annotation being a major bottleneck to dataset curators, the speed of the dataset's release and expansion is quite a lot lesser. And this is a problem for the industry as a whole to progress. So, to this end, tools that automate and speed up data labeling would save not just money, but also time and also have great environmental benefits going forward. This is what we plan to tackle with our work. The key idea here is roads are typically planar and quite well connected. So, if you were to annotate a dataset for road segmentation, our key idea is you might not need to annotate every single point. Instead, what we do is we generate a small subset of candidate points and get labels for them through human annotation. Then use only those labels to autocomplete for the remaining point cloud. So you can think of it as something like you suggest a seeding strategy, and we get labels for the seeding strategy and then use that to propagate labels for the rest of the point cloud. And you can imagine that this saves a lot of time and money because this is a direct benefit for you. By annotating only a fraction, you would save time for the remaining fraction of the point cloud. So in graphical form, this is what that looks like. So what the user would do is upload a point cloud with unannotated points in red over here. We seed the annotation process through generating a set of candidate points for human annotation. And this is typically a very small fraction of the total number of points. So as you can see here in blue, we have selected a few points. Now humans would label only these points. So you would be labeling only the small fraction to get these green labels. So these green colors indicate the points have been labeled. And now we'd use only these three, in this case, only these three green points to label all of the remaining six red points. So this leads to compute requirements being lesser and greener outcomes for dataset designers. Now let's have a look at how we statistically validated this algorithm and how we also realized it in practice. So the key contributions of our work is the quantitative analysis of the efficiency of nearest neighbor sampling for road segmentation. So as you can see over here, what we do for this particular point, for example, is to look at its nearest labeled points and then decide the label for this particular unannotated point through majority classification. And we propose that since roads are typically planar and connected, like earlier mentioned, this notion of labels flowing to the nearest unlabeled neighbors makes sense and is quite performant in practice. We also have an end-to-end system to select candidate points through very fast large-scale search because point clouds are typically in the millions of points. And we autocomplete the annotations through this nearest neighbor sampling. Now, the related work mostly has subsample processing or seeding at training time, wherein they generate some kind of scribble annotations or a subset of points for training the model. We have the novelty in our work is that to the best of our knowledge, this is the first one to do it at testing time, which is quite lightweight and scalable as well. And these are the key main focus areas throughout our work to make it as lightweight and as scalable as possible, as we will see. So here's a look at our methodology. So if you remember from the architecture diagram, there are three main points here. One is to select the candidate points and then to compute the nearest neighbors. And then lastly, to use the nearest neighbors to get the labels for all of these unannotated points, which we also call masked points. So the first step is obviously to recommend a candidate set S from a point cloud P, where P is the input point cloud, where the number of points in S is smaller than the number of points in P. So we tried different methods, and the best method that we found for our practical application is radius sampling, which has the backbone of radius outlier removal, which is a very classical outlier removal technique. So the way radius outlier removal works is that a point is considered an outlier if it has a few neighbors within some predefined radius. We flip the script and consider the other points or the inlier points which has a nearest neighborhood with a radius of a size greater than some predefined threshold. And the motivation behind this is that if you were to label a point, if it has a lot of nearest neighbors around it, the flow of the label of the labeled point would be a lot easier and it would make a lot more sense as well. Another key issue in practice is the budgets. So, for example, on the right here, we have a conversation where people say that I have XYZ dollars to spend for annotation, or I have 9 hours of human bandwidth to spend in annotation. Obviously, SuP-SLiP helps in this by giving you a subset of points where you can realize your budget better. But we also explicitly tackle these kind of questions through our budgeting module. So, the way we model it is we predefine the number of desired candidate points. So let's say 1,000 points for annotation or 10,000 points for annotation, etc. So that's B, the set B. We then have an algorithm which basically is supposed to get the subset of points which is closest to the number of points requested. But we have a constraint here, which is the maximum amount of trials required. So the radius outlier removal or radius sampling takes in a radius parameter. We trial different values of that until we get to max queries number of trials. And typically in practice, as you might imagine, with large scale point clouds, this value is quite less. So this is a kind of unique problem that we have to solve, is if we have a lesser number of queries and we have a predefined number of points, what is the radius value we are going to propose? To that end, we have first found out that this particular model or biased binary search, which is a very classical technique and a very fast technique, actually performs the best compared to some of the other alternatives we tried. So the key points to note here, as illustrated in these red boxes, is what is radius sampling here. We select the number of points in the neighborhood as 100, and then we trial different values of radius. The initial set for the biased binary search is this particular multiplicative threshold, or the number of points requested NB divided by the number of points in total point load NP. That is the multiplicative factor. And we also have a timeout of queries. So if number of queries done till now is greater than a total number max queries, then we just return whatever has been computed till then. Now, the next particular module in this system is the nearest neighbor computation. So we would need these nearest neighbors because for the masked points or the unannotated points, we would need the labels, and we get that through the labels of its nearest candidate points. So what we use is we exploit the proven performance of KD tree or K-dimensional tree in other several use cases and use its very stable implementation in Open3D to perform fast approximate nearest search through KD tree. So this is something that has been documented in multiple case studies, and you can find more information about this in our paper as well. Now, lastly, for a masked point X, which belongs to the set P, but not belongs to the candidate set S, if we find all of its nearest annotation labels, we assign the annotation label through a majority classifier. So we take the K nearest neighbors of each masked point, and then we take a confidence threshold eta. Now, the typical value of eta in practice is 0.5 or a democratic classifier, which essentially means in simple terms, if eta fraction of its k nearest neighbors are labeled as root, this mask point would also be labeled as root. So this uses both of the outputs of the previous models or the candidate points and its hence labels after annotation, and also its nearest neighbors. So hence its nearest neighbors. So once we now have a system to generate candidate points, we compute all the nearest neighbors, and we use only the candidate labels to get the labels for all the masked points. Now let's look at the main use case of our system SuP-SLiP. Now, if a dataset curator like that of Toronto 3D or Paris Lille pictured earlier were to expand to new scans, what we already have is an assumption that there are models trained on the dataset that exists. So let's say Toronto has 4 scans. We would train a model on those 4 scans, and this model already has prior knowledge about the data distribution, about the semantics, and about the point densities of the dataset. Now, if you were to expand the same scan, it would be in the same city, for example, Toronto, and hence the same data distribution. Now, instead of human annotation for the candidate points, what we propose is using the existing model inference on this new unseen scan to generate the actual values. This is a lot faster, and this allows SuP-SLiP to be run in a fully automatic mode. And this is what we'll be pursuing for the rest of these slides. Hence, what we need is we need large-scale datasets, in our case, Toronto 3D and Paris Lille 3D, and models trained on the training section of these datasets. So in our case, we take the checkpoints of RAND, ELINET, and kbconf. And we also have this X-hop strategy. For example, a two-hop strategy means you pass half of the points to the model first, get the outputs, then the second half, and collate the outputs. This performs some speed up in practice, as providing all the points to the model initially for inference takes a little longer. So what you can see here are the F1 scores and accuracies of these models at X hops. Now what we want to see is if the particular nearest neighbor aggregation for the mask point can match these values, because we are taking these as ground truth. Now let's look at the results of the said exploration. So initially, for candidate point recommendation, we suggested radius outlier removal, which guided radius sampling. We also tried two more alternatives of statistical outlier removal, another classical technique, and density-based clustering. So in clustering, what you do is you typically get cluster centers, and we would use that as the candidate points. So to that end, we tried DB-scan, which is another very famous algorithm. What we noticed is radius a lot more aggressive point removals for conventional parameters of the outlier removal techniques. And this is of very high practical significance because this is what dataset designers would like to do, and they would like to iterate much faster. And hence we choose that over STAT. And RAD has much better scalability and way lower runtime for the large scale point clouds that we have in the order of tens of millions of points. As you can see highlighted here, for the L002 or Toronto 3D dataset, radius outlier removal takes around 60 seconds, where DB scan timed out way over 1,000 seconds. And similarly for Lille 2, which is the validation set of Paris Lille dataset, our model took 82 seconds, whereas DB scan again took more than 1,000. Now for the idea of budgeting, wherein you provide a number of points and we try different radius thresholds to get the appropriate value to satisfy your budgetary constraints. We also try different baselines like vanilla binary search, which is a small modification of the biased case we looked earlier. And we also tried out Optuna, which is a very famous hyperparameter optimization framework. And that takes different schedulers and different objectives and the budgetary constraints of number of queries requested earlier, and we have optimized it on the following loss. This is what we call the LJ loss. So n comp is the number of points computed with a particular radius threshold, and n target is what is requested. We take the absolute value and raise it to the power of j. So we have the L1 loss and the L2 loss, which follows from this. Now, what you can see is we took a small data set of 1024 points each corrupted objects from the ModelNet minimal, what we call minimal 40C dataset, and we queried for different ratios of query points and averaged them out. The reason we took the smaller set first for pilot study is because we were able to get results much faster, and hence we could compute the averages much faster. What you can see on the left is that this is the average runtime in milliseconds. We can see the Optina runtime takes a very high order of magnitude time faster to complete as compared to our biased binary search and vanilla binary search. And I can see on the right as well, the L1 loss, which lower is better after computation of biased binary search, is the best. And compared to Optuna's L1 and L2, which is actually quite high considering that these point clouds are quite small. So even in this pilot study, what we notice is that the biased binary search is performing much better than these Optuna baselines, and hence we select that for our analysis. Next, we look at the main questions here, which is the nearest neighbors labels. Are they enough for annotation auto-completion? Are they robust in real-world conditions? To this end, we propose the bit flipping algorithm, which tries to emulate potentially incorrect or irregular candidate point annotations in the real world. Because human annotation or even model proxy annotation is not perfect, what we do is we select a configurable number of points and flip the bits or reverse their labels and give them false labels. So this is kind of like polluting or tampering with the dataset. Next, we look at the So we test this near point cloud P and we take that as ground truth. We pollute this ground truth with a bit flipping attack. We take these particular fractions of chances, and then we mask a large fraction of points artificially. And then the remaining points which are not masked form a candidate set. We get the ground truth labels of this candidate set from the model. And then we take some number of nearest neighbors and some majority threshold values and see what is the accuracy and the F1 score of the masked points labels. What you can see on the right here is exactly that. These are the F1 scores of different configurations of the masked points. And bear in mind, these are averaged out over 70, 80, and 90% masked point, which is quite high. And we also have bit flipping attack enabled here. What we notice is that the performance of our algorithm actually matches the global X-hop ground truth annotation figures for the entire dataset, which means that this model is as robust as we expect. And we also see that taking the democratic zero point 0.5 confidence threshold is a robust implicit defense against even large amounts or 30% of bit flipping. And hence, this is what we recommend for the real world as well. Now, that was to see if nearest neighbors is viable, and we saw that it is. Now, let's look at a stress test or an end-to-end testing of SuP-SLiP. So we have a very low number of queries for a very large point cloud, which is 15 for the candidate points. And for the nearest neighbor aggregation, we use this particular candidate point module to generate a very small candidate set S, which results in a very large mask set M. So we use a small point cloud annotation set to get labels for a much larger point cloud annotation set. And this is at the scale of millions of points. So let's see how that goes. So for the first step of candidate points, we define a metric called SLA or service level agreement, basically, which computes the absolute difference of the number of points computed at the end of the algorithm and the number of points requested, and normalizes it by the number of points requested. So this value should be as close to 1 as possible. And as you can see on the right here, even with a small number of queries, or 15 queries, you can see that all of these SLA values are always greater than 0.999, which is really good in practice. And this is something that dataset designers could reliably act upon. Now let's look at the nearest neighbor aggregation with very large amount of masked points. As you can see, 84% or even 94%. So this means that LIL2 only has 5.8% of points labeled, and we generate the labels for the remaining 94.2% labels. So what you can see here is, as highlighted in blue and red here, taking a small value of eta zero point 0.5 actually gives us really good accuracy and macro F1 scores for both the Toronto 3D and the Paris Lille dataset across different models, RandomNet and KP-Conv, and across different XHop annotation values or annotation strategies. So the conclusion here is that even in the stress test that we have introduced here, we see that nearest neighbor aggregation is really good in practice, and we see that this strategy is something that can be used by dataset curators while expanding their scans. Now let's discuss the implications of these findings. Once we get the road points and we see that we can reliably get an accurate road surface, we can then reconstruct that into a mesh like what you can see on the right here. And the method we propose is Poisson surface reconstruction, which is actually pretty good even on lower end CPUs. And these kind of meshes can guide structural decisions for road surfaces and also be used to guide decisions regarding the driving performance of autonomous vehicles. And also, once we do this particular strategy for a new scan, and if we can get supervision after that, we can then do what's known as a retrospective, or to look at where the model was right and where the model was wrong. Obviously, we can do this in this study because we already have the ground truth of the existing dataset. And why this will help is when the dataset designers were to expand to even more sets, now they can have some areas to pay more attention to, or to have some kind of notions of selective inclusion or human supervision for certain regions. So this is again something that is enabled through our system. Now let's look at some of the limitations. So the limitations obviously in this fully automatic mode is you require a trained model in the same distribution, which would be a bottleneck for brand new data sets where human supervision is necessary. Furthermore, candidate point selection scales with the number of points queried. So it's good in real world conditions, but if you want to query for a large number of points, you might have a higher runtime. Our future work involves further research and new adversarial attacks, including the bit flipping attack and expanding on that, and also expanding to new classes and tackling the long tail distribution of class labels. And lastly, one great suggestion from a reviewer is to look at multiplicity of recommended points. So we are recommending individual candidate points. Their suggestion was to recommend blobs of points, and the annotations or the humans would label the entire blob. So that is also something that we would like to look into in the future. So to conclude, we've seen the efficacy of nearest neighbor aggregation for road segmentation in the idea of annotation auto-completion. These have great implications of time savings, energy savings, and environmental savings for dataset curators. And in the end, more and better data leads to better models, which leads to a safer future in autonomous driving. So thank you very much for listening to this talk and for all of the reviewers as well for their great suggestions. We are open to any questions you might have. You please feel free to email this ID. The code which we are planning to release very soon, it'll be in the QR code on the right here. So thank you again and have a great day.